Fail securely, not openly. Opening. What your system does when nobody is watching. There is a question that most security teams never formally ask, even though the answer to it defines the actual security posture of their environment more precisely than any architecture diagram or policy document. The question is this: when something in your system breaks, what state does it land in? Not what happens when everything works. Not the behavior under normal operating conditions, when the firewall is processing rules correctly and the authentication service is responding and the WAF is in line and the monitoring is collecting. What happens when one of those things fails unexpectedly? When a process crashes, when a network path goes down, when a database becomes unreachable, when a patch disrupts a dependency, when an automation script encounters an error condition it was not designed for. Most systems, if you're honest about it, fail in ways that were never deliberately designed. They fail however the underlying software or hardware defaults, which in many cases means they fail open, meaning they fail in a way that maintains availability at the cost of security. Traffic keeps flowing. Logins keep succeeding. Automation keeps running. The failure is silent. The system continues to look operational from the outside, while the control that was supposed to protect something is no longer functioning. Failing securely is the discipline of designing failure states with the same intentionality you bring to operating states. It means asking for every security-relevant component in your environment. If this fails, what is the safest state it can land in? For a firewall, the safest failure state is one where traffic stops flowing rather than one where traffic flows without inspection. For an authentication service, the safest failure state is one where logins are denied rather than one where users are let through on cached credentials. For a WAF, the safest failure state is one where requests are blocked rather than one where they bypass inspection and reach the application directly. This principle sounds simple. Its implementation is where everything interesting and everything difficult lies. Because the safest failure state for security is frequently the most disruptive failure state for operations. And that conflict between fail-close security and fail-open availability runs through every design decision this session covers. The foundation, 2 types of failure state, and why the difference is everything. When a security component fails, it will end up in one of 2 fundamental states. Understanding the difference between these 2 states and being able to articulate when each one is correct is the foundation of this entire topic. A fail-closed state, sometimes called fail-secure, is one where failure produces denial. The gate closes. Traffic stops. Access is blocked. The system defaults to the most restrictive posture available to it. If you cannot verify something is safe, you treat it as unsafe. The security property is preserved at the cost of availability. A fail-open state is one where failure produces permissiveness. The gate opens. Traffic flows. Access is granted. The system defaults to the least restrictive posture available to it. If you cannot verify something is safe, you let it through anyway because the alternative is disrupting legitimate users. The availability property is preserved at the cost of security. The instinct of most engineers building systems is to default to fail open for a straightforward reason. From the perspective of the people who will feel the failure, a fail-closed event looks like an outage. Users cannot log in. The application is unreachable. Transactions cannot complete. The help desk receives calls. The business impact is immediate and visible. A fail-open event, by contrast, is often invisible to everyone except the attacker who is actively exploiting it. The monitoring does not alert. The users do not notice anything wrong. The business keeps running. The compromise happens quietly. This asymmetry in visibility is what makes fail-open defaults dangerous at a systemic level. Every engineer who has ever built a system under the pressure of availability requirements has been tempted or explicitly directed to fail open rather than fail closed, because the consequences of failing open look like nothing happening, while the consequences of failing closed look like an outage. The fact that something harmful can happen during a fail-open condition, while something unhelpful happens during a fail-closed condition, does not change the immediate incentive structure. But there is a third concept that complicates this clean binary, and it appears most vividly in physical security contexts: the difference between fail-secure and fail-safe. In information security, failing securely almost always means defaulting to denial. In physical security, however, there are contexts where defaulting to denial is not merely disruptive, it is dangerous. An electronic lock on a server room door that fails closed is behaving correctly from a data security perspective, because unauthorized physical access to servers is a serious threat. The same design principle applied to a fire exit door is catastrophically wrong. A fire exit that locks when the power fails is a life safety violation. In physical security, fail-safe means the door opens when power is lost, because human life takes precedence over access control. The security principle is identical. Design the failure state deliberately, but the correct failure state is different depending on what you're protecting and what the consequence of that failure is. This distinction is worth dwelling on because it appears in operational technology environments with real frequency, and it is where the principle requires the most careful judgment rather than the simplest application. We will return to it specifically in the role-based section. Controls, their types, and the implicit deny that ties them together. 3 categories of security control exist, and each category has a different relationship to the question of how it should fail. Technical controls are automated, software or hardware-enforced mechanisms. Firewalls, authentication systems, encryption, intrusion detection systems, access control lists. Their failure states can be designed explicitly in software and configuration. A firewall can be configured to block all traffic if its rule processing engine crashes rather than passing traffic uninspected. An authentication system can be configured to return a denial response if its database backend is unavailable rather than returning a success response to avoid disrupting users. Technical controls have the most designed surface area for deliberate fail-close behavior, which is why they're the primary focus of this principle. Administrative controls are policies, procedures, and governance mechanisms. Change management processes, access review procedures, incident response plans, security awareness training requirements. Their failure states are human behavioral rather than technical. An administrative control that fails open is one where the procedure was not followed, the exception was not documented, the approval was not obtained, or the review was skipped because of time pressure. Administrative controls fail open when organizational culture treats security procedures as bureaucratic friction rather than as substantive risk management. The fix for administrative controls failing open is not technical. It is governance, clear accountability, measurable compliance, and explicit documentation of when a procedure was not followed and why. Physical controls are locks, badges, surveillance cameras, security guards, and environmental controls. Their failure states often involve the fail-secure versus fail-safe tension described earlier. The server room lock that fails closed protects data. The fire door that fails closed kills people. Physical controls require the most contextual judgment about the correct failure state, because the stakes on both sides of the failure mode can be extreme. The principle of implicit deny threads through all three categories and is the technical expression of failing securely in access control. Implicit deny means that in the absence of an explicit rule permitting access, access is denied. It is the default answer to any access question for which no specific answer has been written. This is the fail-closed posture applied to access decisions. If you do not know whether access should be granted, because no rule exists, because the rule evaluation engine failed, because the policy lookup timed out, you deny. You do not guess that access is probably acceptable. You do not grant access to avoid disrupting the user. You deny. This is directly contrasted with explicit deny, which is a rule that specifically names a subject and says no. Explicit deny requires knowing in advance what to prohibit. Implicit deny does not require knowing everything that should be blocked. It only requires knowing what should be permitted. Everything not on the permitted list is blocked automatically. In environments where the set of things that should be permitted is smaller and more knowable than the set of things that should be blocked, implicit deny is both more secure and more maintainable. You enumerate the allowed. Everything else is denied by the architecture itself. Architecture. Designing failure modes before they are needed. The place where failing securely becomes a concrete architectural decision is in the design of stateful versus stateless components, and in the configuration choices made for each security control at the boundary between operation and failure. A stateful protocol or component maintains knowledge of prior interactions. A stateful firewall maintains a connection tracking table that allows it to enforce the rule that inbound traffic is only permitted if it corresponds to an outbound connection that the firewall itself observed being established. This is the basis of the configuration principle that a correctly hardened stateful firewall allows only established and related connections inbound, while permitting outbound traffic to initiate new connections. What this means in practical terms is that unsolicited inbound connection attempts, an attacker attempting to reach an internal service directly from the internet, are dropped without needing an explicit block rule for every possible source IP and port. The firewall's default behavior for inbound traffic that does not correspond to a tracked connection state is denial. The failure mode of the connection state table, if the table is exhausted under a Swine flood attack, for example, must also be designed. Drop new connection attempts rather than processing them without state tracking, because processing stateless would mean accepting connections the firewall has no record of. A stateless component makes no reference to prior interactions. Each request is evaluated on its own merits. This is computationally simpler, but creates a different failure surface. A stateless authentication check that cannot reach its credential store has two options: deny the login attempt or grant it. The principle says deny. The temptation in every production system under customer pressure says grant. The architecture must be designed so that the denial response is the path of least resistance, the default code path when the database call fails, rather than an explicit exception that must be handled correctly to produce the secure outcome. Linux server hardening is a direct expression of this principle at the host level, and it is one of the most common implementation questions in a security interview. Hardening a newly provisioned Linux server means reducing the default operating state of the server to the minimum needed for it to fulfill its designated function. Every service that is running but not needed is a service that could fail, be exploited, or interact with other components in unexpected ways. Disabling unnecessary services means the server's failure state for those services is always the same. They're not present to fail, rather than being variable depending on whether they happen to be running correctly at any given moment. The concrete steps follow a consistent pattern. You begin by documenting what the server is actually supposed to do, its function, the specific services it needs to run, the specific ports it needs to expose, the specific accounts that need to exist on it. Then you disable everything else. Services that the operating system installs by default, but that this server does not need. A mail transfer agent, a print spooler, a web server, an NFS mount daemon are stopped and disabled from startup. Firewall rules using iptables or env tables are written to explicitly permit the specific traffic the server's function requires and to implicitly deny everything else. SSH access is restricted. Password-based login is disabled in favor of key-based authentication. The root account cannot log in directly over SSH, and the list of users permitted to use SSH is explicit rather than defaulting to all system accounts. Kernel parameters are tuned to disable behaviors that are not needed and could be exploited. IP forwarding, source routing, ICMP redirect acceptance. The result is a server whose operating state and failure state are both minimal and explicit, rather than a server whose default configuration includes dozens of services and options whose security implications have never been evaluated. Tools and how they are designed to fail. 4 tools deserve examination specifically through the lens of their failure behavior, because the failure mode of a security control is as important as its operational behavior, and it is almost never discussed in vendor documentation. A firewall's fail-close behavior depends on its hardware configuration. Most enterprise-grade firewalls have a hardware bypass capability, a physical bypass that can be enabled or disabled, which, when enabled, passes all traffic through the firewall chassis even when the firewall software is not running. This is designed for maintenance scenarios where the operator needs traffic to continue flowing while the firewall is rebooted. The security failure mode, when hardware bypass is enabled and the firewall crashes, is that traffic flows uninspected. This is a fail-open condition. The correct default for any firewall in a security-sensitive position is hardware bypass disabled. When the firewall software fails, traffic stops. The outage is visible. The security posture is maintained. The hardware bypass is only enabled under explicit change management control for a specific maintenance window and disabled again before the window closes. The operator who enables hardware bypass for convenience and forgets to disable is creating a fail-open condition that is invisible to monitoring. The firewall hardware shows as operational, but the software processing the rules is not running. An authentication service that loses connectivity to its backend credential store has a failure mode that is directly controlled by configuration. The configuration parameter that governs this is typically called something like fallback behavior or offline mode. If the authentication service is configured to use cached credentials when the backend is unreachable, a common default intended to improve resilience during short outages, it has been configured to fail open. A user whose credentials were valid 6 hours ago can still authenticate even if their account has since been terminated, their password has been reset due to compromise, or their access has been revoked due to a security incident. The stale cache is presenting trust decisions based on information that may no longer reflect reality. The secure configuration is to disable cached credential fallback for any authentication path that grants access to sensitive systems, and to invest in the high availability infrastructure that makes back-end unavailability rare enough that the fail-close behavior rarely triggers an availability impact. A WAF in a fail-open configuration continues to pass traffic to the application when the WAF process fails or restarts. This is a common default because the WAF vendor does not want their product to be the cause of an application outage. The availability complaint that follows an outage caused by a WAF failure is commercially damaging. But a WAF that fails open means that the moment the WAF has a problem, a memory error, a process crash, an overloaded inspection queue, all traffic, including active attacks, reaches the application without inspection. The WAF becomes a component whose failure state is the same as having no WAF at all. The secure configuration is fail-closed mode, where the WAF blocks all traffic if it cannot inspect. The trade-off: potential application unavailability during WAF issues must be managed through WAF high availability. Deploying the WAF in a redundant configuration where a failure of one WAF instance causes traffic to route to another instance rather than to bypass inspection entirely. Electronic locks in physical security represent the fail-secure versus fail-safe tension at its sharpest. A magnetic lock that holds a door closed when power is applied fails open when power is lost. The door can be opened freely. This is the fail-safe design for doors on egress paths, where a locked door during a fire is a life safety violation. A strike lock that holds a door closed using a mechanical bolt fails closed when power is lost. The door cannot be opened without a physical key. This is the fail-secure design for doors on access paths to sensitive areas, where an unlocked door during a power outage is a security violation. The correct design depends entirely on what is being protected. A server room door should fail secure. A fire exit should fail safe. A door that serves both as an egress path and an access control boundary, which exists in buildings that were not designed specifically with these failure modes in mind, requires a solution that satisfies both requirements simultaneously, typically a mechanical override mechanism paired with an alarm that fires when a mechanical override is used, so that any use of the emergency egress path is detected and investigated. Implementation, patching, and the silent fail-open. One of the most underappreciated places where the fail-securely principle applies is in change management, specifically in the process of deploying emergency patches to live systems. The scenario is common enough that it is worth working through in depth. A critical vulnerability with a public exploit has been disclosed, the vendor has released a patch, and the security team needs to deploy it within 24 hours. The pressure in this scenario points towards speed. The vulnerability is known. The exploit is public. Every hour the patch is not deployed is an hour the environment is exposed. The temptation is to push the patch directly to production, accept some risk of disruption, and deal with any issues afterward. The fail securely principle applied to change management says, be extremely careful about which failure mode your patching process creates. A patch deployment that causes a security control to fail, that disables a firewall rule, breaks an authentication integration, stops a monitoring agent, or creates a configuration regression, may produce a fail-open condition that is worse than the vulnerability you were patching. You have replaced a known, specific vulnerability with an unknown, broad failure state. The emergency change process that avoids creating fail-open conditions has 3 stages. The first stage is a test deployment in a non-production environment that mirrors the production configuration. The test is not about whether the application continues to function. Though that matters, it is specifically about whether any security control behavior changes after the patch is applied. Run the vulnerability scanner against the patch test environment. Confirm that the patch closes the vulnerability as expected. Then run a detection validation. Confirm that the CM rules, the EDR policies, and the network monitoring signatures that were active before the patch are all still active and functioning after it. A patch that closes a CV but silently disables a detection capability has traded one risk for a different one. The second stage is production deployment with rollback capability intact. The patch is deployed with a tested rollback procedure documented and ready. The rollback procedure is not optional. It is a prerequisite for the deployment proceeding. If the patch creates an unexpected failure state in production, the team needs to be able to return to the prior state faster than an attacker can exploit the window. The third stage is post-deployment validation. Within 1 hour of the patch being applied to production, a verification scan confirms the vulnerability is closed. A monitoring check confirms all security controls are still operational. The change is closed as successful only when both validations pass. If either fails, the change is an open incident, not a completed deployment. When the system fails in the wrong direction, 3 scenarios. 3 troubleshooting scenarios illustrate the specific ways fail-open conditions manifest in operational environments and how to identify and correct them. The first scenario involves a public website that becomes unreachable from the internet while remaining accessible internally. The immediate assumption is a network problem, a routing failure, a DNS issue, an ISP outage. But the symptom pattern, accessible internally, unreachable externally, points more specifically to a boundary control change. The diagnostic begins at the perimeter. Check the external firewall's rule change log. In many organizations, firewall rules are modified through a change management process, but emergency changes and administrative shortcuts sometimes bypass that process. If a rule was modified or added in the window before the outage began, that rule is the first candidate. Pull it, read what it does, and evaluate whether it could produce the observed symptom. A common pattern is a rule intended to block a specific attack or scanner IP that was written too broadly and effectively blocked all external access to the web server. If the rule log shows no recent changes, the next check is the firewall's operational mode. Has the firewall recently updated its signature set or software version? Some firewall software updates reset specific configuration parameters to default values, and the default value for some parameters is more restrictive than the operational configuration. Check whether the external access rules are still present and enabled, not merely whether they exist in the configuration file. If the firewall configuration is unchanged and the rules are present, the next layer is the ISP and the routing path. Run a traceroute from an external perspective, using an external monitoring tool or a VPN endpoint outside the network to see where the path breaks. If the break is upstream of the organization's own infrastructure, the issue is external and requires ISP engagement rather than internal investigation. The lesson this scenario teaches about the principle is that a security-oriented failure, a firewall that blocked too broadly, produced an availability impact that appeared identical to a network failure. The monitoring that detected the outage did not distinguish between a deliberate fail-close security behavior and an unintended network fault. This is why security control changes need to be captured in change logs that are accessible to the team investigating availability incidents, and why firewall rule changes in particular must go through a review process that validates the scope of the change before it is applied. The second scenario involves a detection system, specifically CM detection rules that stop firing after a log source migration. The organization has moved from one log aggregation platform to another. The migration is considered complete. 2 weeks later, during a security review, an analyst notices that a set of detection rules has produced 0 alerts for the entire post-migration period, despite the underlying activity continuing to occur. This is a fail-open condition in the detection layer. The system did not alert on a failure. It simply stopped producing output, and nobody noticed. The failure was silent. The diagnostic begins with the log ingestion pipeline. Pull the logs from the new source system directly and search for the event types that the affected detection rules are designed to match. If those events are present in the raw logs, the problem is in the transformation or normalization layer, the process that converts the raw log format from the new source into the schema that the detection rules expect. The migration likely changed the field names, the timestamp format, or the event structure in a way that caused the detection rules query to return 0 results even when the underlying events are present. The fix is to update the detection rules to match the new field names and structure. If the events are not present in the raw logs from the new source, the problem is at the collection layer. The new log source is either not configured to emit the event types needed, or the collection pipeline has a filtering step that is dropping them. Trace the path from the source system through every processing step to the CM and identify where the events disappear. The critical lesson is that a detection system that produces no alerts is not necessarily healthy. A detection system that was producing alerts before migration and produces none after, without any corresponding decrease in the underlying activity, has failed open. All the activity is happening. None of it is being seen. The mitigation is to implement detection health monitoring, a heartbeat check that periodically injects a synthetic test event through the pipeline and verifies that the corresponding detection rule fires. If the heartbeat stops producing the expected alert, the monitoring fires on the absence of the expected output rather than waiting for someone to notice the silence. The third scenario involves an automation pipeline that performs threat intelligence enrichment. Each alert that enters the pipeline is enriched by querying an external threat intelligence API that returns an IP reputation score. The pipeline uses this score to decide whether to create an incident ticket. A score above a threshold creates a ticket. A score below the threshold, or an error from the API, marks the alert as low priority and closes it automatically. This pipeline has a fail-open design hidden in its error handling. When the API call fails, due to a rate limit, a network error, an API key expiry, or an API outage, the alert is treated as low priority and closed. An attacker operating from an IP address that is not yet in any threat intelligence database will produce API responses that look like low reputation scores. An attacker whose activity happens to coincide with an API outage will have their alerts automatically closed. The fail-open condition is not visible in the pipeline logs as an error. It is visible as alerts being closed that should have been investigated. The secure failure mode for this pipeline is the opposite. When an enrichment API call fails, the alert is escalated rather than closed. The absence of enrichment data is itself a signal that requires human review, not an assumption that the alert is benign. The pipeline logs the enrichment failure with the alert, routes the alert to an analyst queue with a flag indicating that enrichment is incomplete, and the analyst decides whether to manually check the IP reputation or proceed with investigation based on the other available signals. This is the fail-close behavior applied to automation. When the automated process cannot complete, the output defaults to requiring human attention rather than assuming safety. 3 roles, 3 different relationships with failure. The security architect, the detection engineer, and the security automation engineer each encounter the fail securely principle at a different moment and with different stakes. The security architect encounters it at the design table, at the moment when the failure mode of a system is still a choice rather than a surprise. Their specific challenge appears most vividly in operational technology environments, where the principle produces its deepest tension. An OT device, a programmable logic controller managing an industrial process, intermittently loses communication after a firewall upgrade. The architect is asked to diagnose and resolve the communication disruption without introducing a security regression. The investigation begins with the specific protocol the OT device uses. Industrial control systems use proprietary and legacy protocols, Modbus, DMP3, Ethernet/IP, BACnet, that many firewalls do not understand in the way they understand HTTP or TLS. A firewall that was updated with a new deep packet inspection capability for industrial protocols may now be inspecting this traffic and applying rules to it that were not in effect before the upgrade. Pull the firewall logs and look for drop events on the specific OT device's IP address and the port it uses. If drop events are present at times that correlate with the communication failures, the firewall is the cause. The remediation requires understanding why the firewall is now dropping the traffic. The most common cause is that the new DPI module is validating the industrial protocol's command structure against an expected format, and the OT device is using a vendor-specific extension or a slightly non-standard command that the DPI module rejects as malformed. The secure resolution is to work with the OT vendor to identify whether the non-standard behavior is a configuration issue that can be corrected or an inherent characteristic of this device version. If it is inherent, the remediation is a targeted exception in the DPI rules for this specific device and protocol, not a global disabling of the industrial protocol inspection. The deeper judgment call is about the correct fail mode for the OT communication path specifically. In an IT environment, failing closed is almost always the right default. In an OT environment, a controller that loses communication may respond to that loss by taking a safe state, stopping the process, or by continuing on its last known instructions, which may or may not be safe depending on what process it is managing. The architect must understand whether a communication loss that causes the OT device to fail open in terms of process control is more dangerous than the security risk of leaving the communication path without inspection. This is not a question with a universal answer. It requires knowing the specific process, the specific safety implications of each failure state, and the regulatory framework governing that industrial environment. The detection engineer encounters the principle at the moment when they realize their detection architecture has been silently failing open, producing no alerts not because there is nothing to detect, but because the detection mechanism itself has broken in a way that produces silence rather than error. Their defining contribution to this principle is building detection health monitoring, the infrastructure that detects the detectors failing. A CM correlation rule that has stopped firing because its log source was renamed during a migration is not an acceptable condition to discover 2 weeks later during a review. It is a condition that should have been detected within hours of the migration completing, through a synthetic event injection that tests the full pipeline from log emission, through normalization, through rule evaluation, through alert generation. The detection engineer who builds and maintains this heartbeat infrastructure is the person who ensures that the detection layer does not fail silently open. The security automation engineer encounters the principle at the code level, in the error handling logic of every script, pipeline, and playbook they write. Their specific moment is the one where they are making an exception handling decision. What does this code do when something unexpected happens? The default in many code bases is to log the error and continue. Log and continue is fail open. The automation proceeds, skips the failed step, and produces output as if everything was fine. The secure alternative is to log the error and halt, or log the error and escalate, so that the downstream consumer of the automation's output knows that the output is incomplete or unverified. A threat intelligence enrichment pipeline that logs API errors and continues marks unverified alerts as low priority, just as if the enrichment had succeeded and returned a low-risk verdict. The analyst trusting that output is acting on information that was never actually gathered. The fail-close design logs the error, flags the output as unenriched, and routes it differently from enriched output, so that the distinction is never invisible to the consumer. Case scenario: the bank authentication cache. You are the security architect at a commercial bank. The authentication team has a problem and a solution they want your approval for. The core authentication API, which validates user credentials before allowing access to the online banking portal, depends on a database that stores hash passwords. During the past quarter, the database experienced 2 brief outages, one lasting 8 minutes and one lasting 22 minutes. During both outages, customers could not log in. The authentication API returned an error. The portal showed a generic failure message, and the bank's customer service line received hundreds of calls. The development team's proposed solution is a credential cache. When a user successfully authenticates, their credential hash is stored in a local cache with a 6-hour time to live. If the database is subsequently unreachable, the authentication service falls back to the cache and validates the user's credentials against the cached hash. Customers experience no disruption during database outages. The business problem is solved. You decline to approve the cache as designed. The constraint you are working with is regulatory. The bank operates under financial services regulations that require real-time access control decisions for customer account access. You cannot accept cache trust states for authentication paths that lead to financial transactions. Here is why the cache is a fail-open design that the bank cannot afford, and here's how you explain it. The 6-hour cache TTL means that any change to a credential state made in the past 6 hours is invisible to the authentication service during a database outage. A customer who called the bank 30 minutes ago to report their password was compromised, had their password reset by a customer service agent, and changed their access permissions. That customer's account is now accessible using the old compromised password if an outage occurs before the cache refreshes. An employee who was terminated 2 hours ago for fraud, whose account was suspended immediately upon termination. That employee's credentials are still valid in the cache. The cache does not represent the current state of access decisions. It represents the state of access decisions at some point in the past, and the past may no longer reflect the current reality for exactly the accounts where the current reality matters most. The secure alternative addresses the root cause rather than masking it. The database outages are reliability failures in the authentication database itself, And the correct response is to eliminate those outages rather than to design around them. You recommend a high availability database cluster deployed across 3 independent availability zones with synchronous replication to the standby nodes and automatic failover with a recovery time objective measured in seconds rather than minutes. The probability of all 3 availability zones failing simultaneously is low enough to be an acceptable residual risk for a system of this importance. The cost of this architecture is significantly higher than the cost of a local cache. 3-region redundant database infrastructure requires more servers, more licensing, more network capacity, and more operational overhead to maintain. You quantify this cost in your recommendation and present it against the alternative: the regulatory exposure from a breach that was enabled by stale cache credentials, the reputational damage from a public disclosure that the bank authenticated users based on 6-hour-old credential data, and the operational cost of the customer service burden that the outages themselves are creating. The mitigation for the residual availability risk, the possibility that even the highly available cluster experiences an outage, is an explicit fail-close behavior in the authentication service, paired with a customer-facing status page and a manual transaction processing procedure. If the database is unreachable, the authentication service returns a specific error code that the portal translates into a clear message. The service is temporarily unavailable. Here is the status page showing expected recovery time. Here is the phone number for urgent transactions that a customer service agent can process manually. The customer experience during a genuine outage is better than the cryptic error they received before, because the message is informative and provides an alternative path. The security posture during a genuine outage is maintained, because the cache that would have allowed stale credential lookups does not exist. The risk acceptance document you produce for the residual availability risk is explicit. The bank accepts that during a database outage, customers will be unable to authenticate online. The estimated frequency of this event, given the high availability architecture, is less than 15 minutes per year across expected failure scenarios. The estimated business impact, customer service call volume, customer frustration, potential churn, is quantified. The document is signed by the CISO, the CTO, and the head of digital banking. It is reviewed annually and updated if the actual outage frequency deviates from the estimate. The risk is owned, documented, and proportionate. That is the difference between failing securely by design and failing open by convenience. Closing, the question you ask before you build. The habit that this principle is trying to establish is a question you ask at the beginning of every design conversation, not at the end of every incident investigation. The question is not, what does this system do when it works? Every design conversation starts there. The question is, what does this system do when it breaks? And the follow-up question, which is where most engineers stop too early, is that the right thing for it to do? A system that works correctly under normal conditions but fails in a way that opens access, bypasses controls, or silences monitoring is not a secure system operating correctly. It is a system that has been designed for one state and abandoned in another. The failure state is not less real than the operational state. It is often more consequential because failures happen at unpredictable times under stress when the people who would notice the anomaly are busy dealing with something else. When you write error handling in a script, you are designing a failure state. When you configure a firewall's bypass mode, you are designing a failure state. When you decide what an authentication service does when its database is unreachable, you are designing a failure state. When you build an automation pipeline and decide what happens when the enrichment API returns an error, you are designing a failure state. The discipline is to make every one of those decisions deliberately rather than inheriting them from defaults, from convenience, or from the path of least resistance that keeps the help desk quiet in the short term while creating exposure in the long term. Fail closed when you're protecting access. Fail safe when you're protecting lives. Know the difference. Document both. And make sure the monitoring tells you when either failure mode triggers, because a silent failure is never the secure kind.